Today topic of my talk is terahertz metamaterials and metasurfaces. So as already introduced, so I am currently belong to Mahindra University, Equal Central School of Engineering. This is the front view of our main building, and our labs and offices are in different parts of this main building. Apart from that, we have some other buildings also, and it's spreaded over 110-acre lands. It's pretty green, uh, and it's a residential campus. And I have my group here on terahertz metamaterials and devices. And this is a web page for my group, www.teramed.com, and name of the group is Terahertz Materials and Devices. So the short form is TeraMed. So those who are interested, feel free to visit our webpage. Now, what are our activities? So broadly, our activities can be categorized into three parts. One is terahertz electronic devices, another is material spectroscopy for terahertz, and another is terahertz metamaterials. So in terahertz electronic devices, we try to study terahertz generation detection, and that mainly resonant tunneling diode based devices. So RTD is a very fast device which works on quantum tunneling concept, and it's also a room temperature device, and it's one of the electronic device which can actually generate and detect terahertz frequencies, which is a very high frequency. In material spectroscopy, see, terahertz domain is not very well explored till now. So new materials are required, novel materials, engineering the materials. So what we do is study multi-layers or super lattices of such materials. Also, we study exin 2D materials, exin group of materials, for example, graphene, MOS2, those kind of novel and new with unique properties where you can tune the properties with different external agent. So that also we do, we study for the terahertz responses. And another bigger focus of our group is on terahertz metamaterials that can further be divided into three parts. That is, one is active metamaterials, another is functional metamaterials, another is sensing metamaterials. Although I am dividing them into several parts, but it's not that straightforward. They are very much overlapping. The activities are very much overlapping. So in case of functional metamaterials, again, we work on different aspects of metamaterial. For example, Fanout Resonance, then electrometric induced transparency or quantum effect metamaterials, then metamaterials for polarization optics, that is polarization conversion, broadband metamaterial, which has a big influence in upcoming 6G communications, in terahertz communications, near field electromagnetic interactions. So what happens that metamaterials are all resonator based. So now, depending on the interaction between the resonators, that interaction is of course very near field interactions, the properties can be tuned. So that also we do. So in this talk, I'll mainly cover this functional metamaterial aspect. I will not go for terahertz generation detection or materials, but mostly functional metamaterials. In a way, it is the passive metamaterials, not even active metamaterials, that I will cover several problems from this domain. So now moving forward, let us see what is metamaterial. So you know that in the last 20 years, maybe very active in metamaterials, which showed tremendous potentials. So one of the reason many of you might have seen this picture of Harry Potter's cloak. What it says that you see that reflection, in the reflection the body is missing. That means the body is cloaked. So is it just an is that a idea or assumption or imagination, or is it really possible? So most of the cases people have taken example of this as Harry Potter's cloak, but I was just wondering what about our own movie industry. So there was several examples. One of them was Mr. India, where Anil Kapoor was made invisible, which is also an example of cloaking. But our target or our aim or our trend is always to see, for example, from abroad. But however, there are plenty of good examples in our own country. Anyway, so how to make them cloak, how to make it invisible. So to make it invisible, what you need is metamaterials or metasurfaces, which is kind of supernatural or beyond nature or beyond our imagination. We generally cannot think that something is invisible, but can one make it invisible? So metamaterial or metasurface has that potential to make the things invisible. So at the heart of that is basically how you play with the electromagnetic waves. That is what can make things observables invisible. Just like at one example, but that is not the all. This is one of the most attractive example which made metamaterials very popular. But apart from that, there are tremendous huge amount of applications are possible, and I'll shortly go through them. So now, how to make something invisible? So you see that the reflection is not a natural reflection. It's according to Snell's law, it should bend in this side, but it is bending in the opposite side. So how it is possible? If your refractive index is negative, then instead of bending to this side, that the light can bend here like this, and then again it can bend, instead of bending in this side, it can bend this side. So these things, if one can tune, one can design metamaterials in a proper way, then one can manipulate this propagation of light. So as a natural consequence, the cloaking was one thing. You see that this is the object which we wanted to cloak, and how one can cloak it. If the rays of lights are coming like this, and if it is stopped or reflected from this object, then you see that object. But let's say if we have some magic material or magic coating which can bend the light like this, then light can travel like this, and some eyes here won't see this object, but it will see this side. So this is the concept, and metamaterial was supposed to do this kind of thing. So this is the concept of cloaking. So this is the object which was to be cloaked. So now you have this ring. Now this ring has the property which can bend the light just like this, with this concept. And if it can bend the light, then any electromagnetic wave, this is the source which is coming from here, then instead of reflecting or refracting from it, it will go past, it will bypass this object and can go to the other side, and hence you cannot detect this object. So this concept is used in for example, in Air Force, where you want to make stealth technology, where you want to hide your aeroplane from, or fighter planes from enemies' radars, enemies' eye. So these kind of things are possible using metasurfaces or metamaterial. So metamaterials is basically the 3D concept, and when you bring it down to 2 dimension, then that is called metasurfaces. Now let's see scientifically or technically what is metamaterials or metasurfaces. So first of all, this is a material. And why it is called material? Because this is the metamaterial and this is a natural material. So you see that like natural material, what happens in natural material? Atoms are, or molecules are periodically placed with some discipline. So similarly in metamaterial, these resonators are each meta atom, and they are also periodically placed. Now the definition goes like this: metamaterial is an arrangement of artificial structure elements designed to achieve analogous and unusual electromagnetic properties. Now one of the important thing is, this is of course artificially structured element, and another thing is the electromagnetic wave that you use to excite this artificial structure, its wavelength has to be much bigger than the this lattice parameter A, that is the units distance between the unit cells. And this can be treated as an effective media. So what does it mean? That we don't speak about single resonator or two resonator, we speak an array of resonator, where the through the electromagnetic wave is going, and it sees a whole array as a coating or as a effective as a medium. So this whole metamaterial thing or that metamaterial surface can consider as an effective media. Depending upon the design of these resonators, one can achieve negative permeability, tunable permeability, tunable permittivity, and all these properties, and that helps to control the light. So because of the because of the convenience of these metamaterials, you see that it has enormous applications across the scientific spectrum. So not only it's a matter of physics or electrical engineering, but it has application in electrodynamics, acoustic, mechanical, and of course, micro nano domains, even in bigger, in stealth technology, just everywhere almost these metamaterial concepts are applicable, and it helps to manufacture, prepare novel functional devices to suit our requirement in the coming times. Now, although we know or heard that the Spendry first time proposed this metamaterial concept in 1999, and in 1967, Veselago actually theoretically first predicted that this kind of materials are possible. And after 1999, the research actually went very high, and people were became very much interested. But what we see that at the heart of this metamaterial is the resonator, and the resonators are nothing but wires with some twist or with some modification. And this concept of wires and artificial media, this was actually first introduced by 1898, 100 years, more than 100 years before John Penry proposed this metamaterial thing by Acharya J.C. Bose. So what he did at that time, in spite of all this limitation in experiments and funding and all these things, he made a very simple experiment. He took this jute, this bunch of jutes, and he put them like this. And if he launched a light, in his case it was microwaves, and then if it couples in one end, when it comes through the other end, he found that the light is actually polarized. So this is nothing but probably the first demonstration of artificial media. And IEEE recently, at the 100 years, that is in somewhere in the end of the last century, they actually acknowledged that Jagdish Bose's work, which was done 100 years back, was the pioneering work, and that started this millimeter research. And in a way, it acknowledged the inception of artificial media. Nevertheless, with this history, now let us see what is happened in last 15-20 years in this metamaterial. So first, this Penry proposed these structures of split ring resonators and these dipoles, and there he showed that negative permeability is possible. Moving ahead in 2004, from Jiang Zhang's group from Berkeley, they showed Terahertz response from artificial ring resonator, and this structure became later very popular. And there they showed that this permeability can be controlled, the real and imaginary part. So moving ahead, there are many variations of structures came into picture. So this is a very good review article. Those who wants to read can read. And then there was something like active metamaterial concept also arrived in 2006. That was published in PRL. So what is the active metamaterial? That one of the problem with metamaterial is that after fabrication, these devices are these properties of these devices are fixed. So that limits its functionality, that limits its applicability in practical cases. So then people started thinking how you can tune the properties depending on your need. So here in this work, they showed that using photons, that the properties can be controlled. So if this is the resonances at some particular illumination, and when you illuminate more, then these two resonances killed and this new resonance actually evolved. So this means that, let's say, very simplistic example, if you want to use it as a sensor, so you are not bound, you are not limited to use that sensor at these two frequencies, but using that photon you can change it to the other frequency. Now coming to this picture, you see that this is a circular disc, this is the dipole, this is a more complicated structure by Capasso from Harvard. This is a swastik-like structure, this is the whole array, this is the coupled resonator. You see one dipole and one dimer, they are coupled. This is our kind of circular dimer. These are just simple dimer. So numerous structures came. So why these numerous structures are required? Because it has so much of application. It is such a convenient concept that one can apply it to almost in many functional cases. And depending on that, you can tune, you can design your structure. Now coming to the terahertz thing, what I do, I mainly do metamaterials for the terahertz domain. So there is this terahertz domain is very interesting. So you see that this is the microwave domain and this is the light domain. So where you have the visible here, infrared, ultraviolet, X-ray. Now the problem with this terahertz domain is we don't have natural sources. Since you don't have natural sources, you don't have natural detectors, you don't have natural components, natural photonic components, optical components to control, to guide the waves. But however, so for example, sunlight is a source of visible wavelength. In sunlight, you have parts of infrared, ultraviolet, then you have many lasers for these frequencies. And you also have many source, gun diode, and etc. for microwaves. But terahertz, it is lacking because of the unavailability of the sources and detectors. So, however, this terahertz is a very interesting domain. For example, 98% of the waves in space that we capture actually composed of terahertz domain. So apart from that, there are a lot of functional and practical applications. So industrial NDT, defense and security, biomedical, and different other application. So for example, terahertz can pass through dielectrics almost without any loss. So this can help you to non-destructive testing. So for example, the composites and maintenance, pharmaceutical quality check, even in control of semiconductors. In semiconductors, when we make the chips, there may be a lot of faults come up. So cracks come up. So how to detect them? Terahertz can do that. Thickness measurement. In defense and security, of course, in homeland security, it has a big, huge applications. For example, in the airports, one can detect the concealed weapons, because terahertz can go through the cloths, but it cannot penetrate through the metal. So one can image if some hidden object or hidden metal or hidden arms are there. So you see that. And then in medical fraternity, there are huge application of terahertz for detection, mainly and tissue culture and all these things. But as I said, the major limitation with terahertz is it does not have a natural source. It does not have a natural source, natural detector. So what do? There are two ways. Although it has so much potential, but because of the lack of this natural source and detector, this domain is not studied well. This domain is not explored well. Of late, we are trying. Last 15-20 years, this terahertz has taken a jump, and a lot of work is happening, but still a big long way to go. So now one way to approach terahertz is through microwave. Another way is through the optical side. So in case of microwave, what people mainly use, they try to use faster and faster devices. So for example, quantum tunneling devices, and they are also they cannot go fully into the terahertz because electron speed is limited. Then they try to use the nonlinearity and generate the harmonics and then entering the terahertz. But in that case, the power reduces a lot. So from the optics side, people try to use the basically the concept of beating frequency, so overlapping two different frequencies, and then from that beat they try to generate terahertz, and using reverse engineering they try to detect terahertz. So you see that all are these indirect techniques. And even if you generate and detect, then you need to make the optics, you need to make the components, lenses, mirrors, polarizers. How you do that? So metamaterials is, or meta surfaces can fill up this gap. Metamaterial meta surface which can play with the electromagnetic waves, so it can play with the terahertz waves also, that can help you to make the components. So that is the reason, this is the motivation for me for studying terahertz metamaterials in details. So moving ahead with this background, now I'll discuss some of the recent research problems that we have pursued in last 1-2 years. Of course, we cannot present all our works, but I have taken 2-3 signature problems that I will describe. So beginning of this year, we published this paper, Magnetic Wire Transverse Magnetism in a One-Dimensional Plasmonic System, in optics later. So let me explain what this work. So what is the motivation behind this work? So we all know about the plasmonic wire, which can support electric mode under applied electric polarization. So how to visualize a plasmonic wire? So this is just it is nothing but a current carrying wire, where you have, if you put voltage one end, positive side one end, and then you decide the other end, then what happens? Electrons flows, since it is a conductor. And because of the electron flow, you have the current flow. So since you have the current flow, then what you have the magnetic field lines circulating the this wire. So this is a visualization of plasmonic wire. So plasmonic wire are nothing but where you have a light matter interaction and energy, light energy couples, and then there is a electric current. In high frequency, it is actually alternating current, but nevertheless there is a electric current flows across that wire. Now the problem with this kind of structure is, plasmonic wire, is that the field is surrounding the wire. Unlike electric field, it can generate from plus side to minus side, but magnetic field is always surrounding the wire. So how do we can get the artificial magnetism, but how can we get a magnetism or magnetic field lines which is coming out from the from a plane carrying conductor, carrying conductor? So for example, in that case, what we can do, if we have one wire like this and if we have another wire like this, then you see that this fellow will induce a magnetic field like this surrounding, and this fellow will induce a magnetic field like this, and then you see that kind of a normal magnetic field may be achieved, right? Or another way is, if you bend a simple straight plasmonic wire into a ring resonator, then what happens? If you can induce current, then you have a circular current, and hence the magnetic field lines are coming out from the plane of the resonator. But you see that all these cases, either you need to twist the plasmonic wire, or you need to change the shape of the plasmonic wire, or you need another plasmonic wire, and you can get the artificial transverse magnetism. But can one get a transverse magnetism directly coming out from the resonator or coming out from the plasmonic wire? So you see that this also this is the basic theory from Maxwell's first and second law, where you see that in case of electric field, you see if you have a charge, then it's just coming out. But in case of magnetic field, it does not come out directly. It does not come out. Nature is not transverse, but it is circulating around this. But in this problem, what we try to do, we try to hit this issue, that can we design a plasmonic wire in such a way, so that the fields, magnetic fields, can come out directly from the plane of the wire, or in other way, in other words, that is transverse magnetism. So what we did, we designed two dipole in this way. So length of one dipole is L1, the length of the other dipole is L2, and if here I have shown only one picture of one sample, but we had 5 samples. So how the 5 samples are differ, you have to extend your imagination a bit. So in sample 1, this is the first sample where L2 is equal to L1. That means that both of them are of the same size. In the second sample, where L2 is 90 micrometer, that is, this is shrink in this dimension. In the third case, it becomes 80 micrometer. In the fourth case, it becomes 70 micrometer. It is shrink further. And in the fifth case, it becomes 65 micrometer, and it sinks even more further by 35%. Now, what we see, this is the simulation, and this is our experiment. So, needless to say that experiment is pretty well following the simulations. So, what we see that in first case, it is just a one dipole type resonance. In the second case, you see that there's sharp asymmetric high Q resonance is appeared here, and also the dipole then almost the similar strength, then the strength is changed kind of, and then finally what we see that a higher frequency mode is very narrow, but the lower frequency mode, which was earlier the narrow and asymmetry, it has become kind of dipolar symmetric set. So with the change in L2, so what we did in this experiment, we kept the L1s fixed, but we changed the L2 slowly. So from 0% asymmetry to 35% asymmetry. Now we examine each of the cases. So in first case, so in L2 was 100 micrometer, that is, this is the L1 length of the dipole, this is the length of the dipole, both are same. In that case, you see that we got only one resonance, which is a broad resonance, and this is the surface current distribution and electric field distribution. It simply indicates that the resonance is a dipole resonance or dipolar mode. When you move to 10% asymmetry, that is 90 micrometer size of the second resonator, what we observe, there is a small there is a resonance appeared that we call LMM, and because left metamaterial mode, and this we call RMM, that is right metamaterial mode. So in left metamaterial mode, this is the surface current distribution and this is the electric field distribution, and this is the surface current distribution. In case of right MM, this is the electric field distribution, and this is the surface current distribution. So what we see that in case of right metamaterial mode, these surface currents are all in the one direction. So we call this that it's a dipole mode in the symmetric dipole mode. But in this case, what we see that in one resonator, these currents are in the going from bottom to top. In another case, it is from top to bottom. So these are like a asymmetric dipole. Now moving ahead, if we increase the asymmetry to 28%, you see this is the real picture of the structure of the metasurface. Of course, one unit cell. Then you see that this is the LMM and this is the RMM. And what we see in this case, that in LMM, these surface currents are anti-dipole kind of. But in case of right metamaterial mode, we see there is a very interesting thing, that in the right resonator, although the current is like a dipole, but the left case, it's kind of a circular current across the resonator. So this is what we are actually targeting for. Moving ahead at 35% asymmetry, more asymmetry, what we see that this circular nature of this current across one resonator has become much more prominent, much more stronger. And this means that from simple electromagnetic theory, the magnetic field should be, it is forming like a loop and coming out from the plane of the resonator, which is nothing but the transverse nature. So moving ahead, we captured the side view of the magnetic field distribution. So what is the side view here? You can see in case of the side view, You see, this is the right resonator, and this is the left resonator, and this is the magnetic field distribution. You see that the magnetic field lines are as if coming out and is as if it is entering. So this makes that the kind of transverse field across the resonator. Okay, so till now, which was believed that you need to make special structure for to get this transverse magnetism in metamaterials, but we have shown that that's necessarily not the case always. With suitable designing, with suitable interaction between the resonators, one can achieve a situation where field lines may be coming transversely. Field lines can be oriented in the transverse fashion with a plasmonic wire. So now, in order to prove whether we really seeing one-dimensional system or not, what we did, we further changed the aspect ratio of the resonators, and we moved to 100/1 aspect ratio. That means, although the asymmetry is kept constant at 35%, asymmetry is the difference between these two lengths, but we shrink this other dimension, and this length to width, we made it to 100:1. So that if there is any confusion about the one-dimensional claim about the one-dimensional system, that we have settled here. So with this 100:1 aspect ratio, and in that case also we have seen that in this right resonator mode, you can see that the current nature is circular, and when we see the magnetic field in the XZ plane, XZ plane means from the middle, if you cut it, and if you see from others from a tangential side to this picture, then this is the picture that we get, and you see that the field lines are behaving like this. So it is normal to the resonator. So that means that it proves that the fields are transverse. So now, of course, this is a concept, physics-wise it is interesting, but what is the advantage? We have shown that anapole mode or terahertz anapole mode can be excited, can be achieved using this type of structure. So what we do, what we studied for the proof of the concept, that two dipoles, but if we put another dipole beside that, then what happens that at this magnetic transverse mode, this magnetic field lines which is generated in this dipole and which is generated in this dipole, they are in the opposite direction. So this is the surface kind distribution. You see that in the middle, this is a pure dipole-like configuration, but here this is a circular configuration. Here it is a circular configuration, and if you see the field lines in this case are going in this case it is coming out. So it is forming a these magnetic field lines are constructively interfered and forming a loop, and which means that, and the electric field that we have, that is from, if this side is plus, this side is minus, then the electric field is across these two ends. So if you see the electric dipole, which is in this direction, magnetic dipole in this direction, and this nothing but the characteristic of an anapole mode where the energy is strongly confined, and because of that, this very sharp peak is observed. So necessarily not that we have to see that circular current distribution or this transverse magnetic moment in a single wire, but with some engineering, one can achieve this kind of interesting things. So what we have shown in this work, basically, that against the conventional belief that artificial magnetic moment or transverse magnetic moment cannot exist in a single plasmonic wire, that's actually not correct, and with some modification, with some trick, one can actually excite this kind of transverse magnetic moment. So what is the direct consequence? The direct consequence is when you get a circular current or transverse magnetic moment using a simple dipole that can make your photonic ICs or electric ICs even much more simpler. So the more compactness is possible. You do not need to go. So you know that for getting an inductance or magnetic property, you need to make coils and go for more complicated structure. But that's not always the case, and one can get using a simple dipole. So this should help further miniaturization of photonic and electric ICs. So you see that this concept can have a lot of applications in near future. So now with that, I will move forward with another problem that we have worked recently, that is on Fanout resonance. Fanout resonance is a very interesting physical concept which was first proposed by Ugo Fano in 1961. So what it says in case of Fanout resonance, it says that if you have a broad spectrum, and on top of that, if you have a narrow resonance, then interaction between them can lead to a very high quality factor asymmetric line shape resonance. So, and this kind of situation can be explained or can be modeled using coupled oscillator theory. So what is that? So for example, if you have equation for one oscillator like this, which is driven by an external force or external factor, and if the other one, if you don't have this driving, that external driving, and if they are coupled, then that system gives rise to a couple resonance modes where one resonance is asymmetric high Q and another can be a broad. So this is what is happening here. You see that this is a narrow band high Q factor resonance and this is a broad resonance. And because of this narrow band resonance, which is an asymmetric line shape, and this is identified in metamaterial as a Fanout resonance. So this is the pictorial representation of this situation where you see that you have one mass, you have another mass, and they are coupled, and these both of them can oscillate. But if you apply force to one and another one, if no force is applied, then this concept is applicable there. And how they resonate? They don't resonate at single frequency, but they resonate at two different frequencies. And one of that frequency is a low loss resonance, and another mode is a high loss resonance. That low loss resonance is identified as Fano, and the high lossy mode is identified as normally dipole in metamaterial community. And this is the surface current distributions at these different resonances and at the transparency peak. So with this concept, it became pretty popular. Initially, this was proposed by Nikolai Zeludev's group from University of Southampton. There they call it trap mode, and then later it was known as Fano mode, trap mode, dark state. So it had different names. So at the heart of this concept is asymmetry. So whatever be the structure, you have to apply some asymmetry. So for example, if your this hole is at the middle, you may not see Fano resonance. But if you can shift it and introduce an asymmetry, Fano resonance can appear. So similarly here, if these cuts are at the symmetric position, let's say at the half position, separating it into two equal length semi-resonator, semicircular resonator, then you don't see Fano. But as soon as you introduce this asymmetry, there is a chance of appearing Fano. So the same case here, if both are same, then you don't see. Then if the size is different, so same case here, you see that if this gap and this gap, they are exactly aligned at the middle, that is a symmetric system, you don't see. But the moment you introduce the asymmetry, there is chances of development of Fano mode. So now what is it? That structural asymmetry is important, that is must. Also, having structural asymmetry does not guarantee that you will see the Fano mode. So structural asymmetry, then you have to hit a particular point, then one can see a very strong and reasonable Fano mode. So then we started thinking how one can excite a, a Fano in a symmetric, at least geometrically symmetric structure. So if that happens, that can be done, then the best the advantage is that we can overcome the fabrication uncertainty condition, because although we design a structure with a particular asymmetry, because of the fabrication intolerances, you may not achieve it, so you may not get the best Fano mode. But if it is a symmetry structures, then this can be to some extent immune to those asymmetry fabrication tolerances. Although there will be fabrication tolerances, they are also, but it may not happen. It may not part of that to that extent. So for the motivated by this concept, what we did, we proposed this stacked resonators. So what happens here, that you have a silicon substrate, on top of that we have a bottom resonators dipole of same size, then we have a polyamide, and on top of that, absolutely aligned, we have another resonator of the same size. Now although these resonators are of the same size, but electrically or optically their characteristics are different. Why their characteristics are different? Because the top resonator is seeing different environment, and the bottom resonator is seeing different environment. So therefore their characteristic frequencies, their characteristic resonances are different, and hence they can overlap with each other, considering one as the background and another as the as the driving mode, and can give rise to Fano modes. So this is what is explained here. So you see that this is the top, this is the bottom, but when they couple, when the distance is very small, then it can give rise to two modes. In one case, you see the surface currents are in the same direction, so dipole mode. In another case, they are in the anti-parallel, so this is called the Fano mode. So this is our fabricated structure. This is the artistic view, and what you see, you see that this is the one unit cell. So the bottom one cannot be seen. So this is the top result. Then underneath there is polyamide, and underneath there is the bottom resonator. This work was published in Physical Status Solidi, RRL, Rapid Research Letter, 2 years back. And what we showed there, this is the theory and this is our experiment for this kind of structure. And you see that there is a broad resonance evolved here at this low frequency, and whereas this narrow resonance is evolved or appeared at the high frequency. This is the theoretical calculation using coupled oscillator model, using this coupled oscillator model. And then what we had, this is our experimental data. So moving ahead, when we examined the surface currents, what we observed that at this low frequency mode, which is broad mode, these are two dipoles. But whereas in case of that high frequency mode, what you see that anti-parallel current, and confirming this as the Fano mode. And this is the picture that just I explained. So this unique concept of Fano in a symmetric structure actually pretty well highlighted and cited also. And that time it received the journal cover page in PSS RRL. So moving ahead with this concept, then what we further observed, that there is this very strong field confinement in the polyamide. So you see that if we capture the field confinement at the dipole mode and at the Fano mode, that means here and here. So what we observed, that in the dipole mode, the field confinement is not that strong. It is somewhere here where the rate is the maximum. But however, at Fano mode, we see there is a huge, strong field confinement is happening in the film. So now that is a very advantageous situation for us. Why is it so? Because when we use this single gap split ring resonators, which is very popular, which is well established, in that case the field confinement is mainly take place here in the split gap. and you see that in this area there is no field confinement. So if you want to use it as a sensor, so what you need, that strong field confinement. Field confinement is stronger, then that means we have a you have a better sensor, you have a more sensitive sensor. So however, this field confinement may be strong, but it is limited to a very small place. But in this case, because of this broadside coupling between the bottom and top resonator, the field confinement is almost all across the resonator. So that means that effective area of sensing is increased. So exploiting that concept, we checked the sensing capability for this kind of cavity, and also this is a deep subwhelming cavity, because you see that this is this thickness is only 2 micrometer, whereas at 1 terahertz the wavelength is around 300 micrometer. So you see that it is almost 1 by 150 times smaller area. So although the wave which we are using is much longer wave, but the field which is confined is in a very small area we can achieve. And what we observed here, that this is the sensitivity, this is the figure of merit, which is nothing but sensitivity by bandwidth, and we observed that a record high 610 gigahertz per refractive unit sensing can be achieved. So this unique scheme was later, this work was published in JPD, and it was highlighted in Twitter by JPD. It was highlighted by JPD in Twitter, saying that this is a very novel new metamaterial scheme which can be extremely advantageous for sensing related applications. So moving ahead, we have seen compare the electric field distributions also, because that is the key here for the sensing. You see that at 1 micrometer dipole dip cannot confine energy very strongly, so you don't go into detail. At Fanout dip at 1 micrometer spacer, this is the field confinement. These are 2 micrometer, 4 micrometer, 8 micrometer. So to see that 2 micrometer was kind of optimized point. There we had the maximum field confinement, and with this concept we further move ahead in refractive index sensing, and we did it for 1.4 to 2.0 refractive index, and what we observed, that record high 1.4 terahertz 1 terahertz per refractive index unit sensing is possible. Of course, we found that T02 micrometer is the most optimum point. Beyond that, what happens that the distance increases, so the interaction between the resonators also reduces. So the field confinement is not as strong as it is in case of T02 micrometer. So there we hit almost 1 terahertz per refractive index unit sensing. So then moving ahead, we did chemical sensing also. With this scheme, for example, water, IPA, ethanol, different things. And what we observed, a very interesting thing, normally what happens in metamaterial sensing schemes, that one uses, since we have this frequency dip, so the frequency shift in frequency dip is used for sensing. But for chemical sensing, what we have observed, that it is just not the frequency shift, but the intensity contrast can also be useful. And this, you can see that intensity contrast also exploited for towards the sensing capability. So moving ahead, what we did, we have seen the lattice mode effect on resonance hybridization in this type of multi-layer metamaterial or meta surfaces. So what we did here, you see that this is the artistic view and this is the real samples. So as I explained, you have a bottom resonator, then you have a polyamide, then you have a top resonator. And in these situations, in these cases, if the periodicity is changed, if we change the periodicity, then what happens? then how the characteristics, transmission characteristics are affected. And when you change the periodicity, that means that we are actually triggering the lattice mode. And this lattice mode can tune, can modulate, can modify the these resonances. So what we have observed that with the change in this periodicity, these resonance shapes are changed. So this is again, this is our simulation, this is our experimental, and this is our analytical solution using the coupled oscillator model. And for different periodicity, that when you vary the periodicity in the x and y axis, x and y direction, we see that there is a tremendous change in line shape happens. So, and then again, similar style, we have found out the electric field surface current distribution, which is the best tool for us to identify a nature of a resonance. And what we observed that for the low frequency, you see that this dipole, this is Fano, and here both are kind of Fano, and here you see that the low frequency Fano and the high frequency is dipole. So it shows that playing with the dipole mode, your resonance can switch from dipole to Fano, Fano to dipole. And the same thing we have seen in case of the periodicity for the heading periodicity for the x direction. This for the y direction, this is for the x direction. How much time I have? Hello? Anybody listening?
Yes, sir, of course.
Yeah, how much time I have? 5 minutes more?
Yeah, you can carry on, sir.
I'll finish in 5 minutes. So these are the things we have done, and apart from that, we worked in some toroidal, some dark states excitation. So this is dark state excitation in planar structure. You see that these are symmetric resonator, and then we incorporate this asymmetry by including this plate, and then more. And what we have found that in case of symmetric structure, this is the spectrum, and when the moment we incorporate this asymmetry, then a sharp mode is coming. And of course the red line is the simulation, black is the experiment, and this high quality resonance at the lower mode that we have further exploited in different cases. So for example, in sensing, and also we did another thing, that if in such cases, in this type of asymmetric cases, if we play with the inter-resonator distances, then what we observed that a very sharp resonance was coming with high quality factor. And then when we explored that further, we observed that this is the nature of the magnetic fields. Here you see that the current is anti-clockwise. This case, the current is clockwise, anti-clockwise, clockwise, anti-clockwise. So you see that the field is going in, going out, going in, going out. And what we observed that these and these were forming a closed loop, or a constructive interference are happening between the magnetic field lines. And here also across the unit cell, these constructive field lines were constructive interferences are happening, and that gives rise to a strong confinement of energy. So this is the picture. You can see that. You see that the magnetic field lines are across the resonator, they are confined, and that explains that the appearance of this strong resonance mode, or high quality factor mode. And that we have further seen that the quality factor went up to close to 200, and with a high figure of merit around 80. And that we see that for the toroidal mode resonances, this is much higher, but for the quadruple resonance, it is not that higher. So this is the quadruple mode, and this is the toroidal mode. So this is forming like a magnetic toroid. So from there, because of that, we call that this as a toroidal mode or this resonance. So yeah, that's all from my presentation. So this is the acknowledgements. Of course, I must acknowledge my students who worked on all these problems, did the experiments, did the simulations, did the modeling, and we cannot do research without funding, without money support. So I'm fortunate to have a few CRB projects so far, and also our university supported me to develop several programs. Also, some of professors and scientists from TFR and IT Delhi, Professor Prabhu and Professor Barsne, time to time, I was fortunate enough to collaborate with them. That helped me, and this is the people who are worked with us. And Jagan Mohan graduated, and now he shifted to move to Korea. And Dr. Monica Devi is working with me, with us, and many of the other PhD students, they are working now. So if you want to have more details, feel free to visit teramet.com and feel free to drop me an email.